unlisted.
Там написано открытый.
Ну ладно, да, сейчас.
Открытая трансляция.
Дальше я сделаю, да, если.
Вот она выполняется настройка.
Угу.
И тогда нужно всем ссылочку разослать. Тем, кто не успел войти, сейчас мы запустим.
Сергей, давайте, если будет меньше там 80 человек, это вообще не нужно. И я это сделаю, если будет уже близко к пределу.
Нет, там регистрации больше 100 было.
Да, но обычно не все люди подключаются. Я это сделаю, когда мы приблизимся к пределу. Или, может быть, это не будет актуально. Stephan, also thanks from the young scientists of ISBM for agreeing to have this talk for us.
I'm very pleased and also honored that I was asked to give this lecture, and I hope I can also fulfill the interest of the participants. Just a question from my side: how many participants do you roughly expect?
Usually we have like up to 120 people, but quite a few people were scared of the first talk of the series in English. So like I think it can be decreased significantly. That's why we try these new features for us, like live transcription. We try to run auto translation, but
okay.
I have not succeeded. So we only have a transcription. So, and I hope it will be like 50, 70, 80 people.
Okay. Oh, so Agnes is coming back.
Yeah. Sergey, your mic is off.
Ah, okay,
Yes.
you can hear me.
Yes.
The problem that I hear the translation and I hear Zoom, and it's this kind of delay.
There should be a delay. Just
yeah, but how can I close the?
You can pause. You don't need this translation running in your tab of browser. Just pause it.
Okay, great. So I just posted browser and it works now. Yeah.
We have like 30 people in waiting list, but
yeah, I think we should already allow people to come in. Yeah.
And how we, okay.
Actually, we have about 110 registered participants, and we can allow to come in 100. All the rest should look in the
YouTube.
In the YouTube. Daniel, have you sent a link to YouTube?
Not yet. I explained it to you. Could you hear it if we
okay
have...
okay, so I invite all the participants here.
Okay.
Oh, sorry. Sure. Okay, Daniel, you can do it as well, yeah? Or I need to.
Yes, I can.
Your co-organizer.
Yes.
Yeah, right.
Yes. I will do it like during the whole talk.
Okay.
but we still have to wait at least like 4 minutes.
Yeah, because it's 3 minutes left. Уважаемые коллеги, мы через несколько минут начнем. Я вначале скажу по-русски, а потом переведу на английский, и дальше у нас лекция будет Стефана Кирхмайера на английском. Снизу вот, в принципе, идут субтитры.
Almost 50 participants we have at the moment.
Коллеги, у меня на часах 15 часов. Можно, наверное, начинать. Stefan, it's already 3 o'clock in Moscow.
Okay.
And so we can start. I will start in Russian by introducing you and then translate in English.
Sure.
Уважаемые коллеги, я Сергей Пономаренко, директор из PMRAN. Рад вас приветствовать на нашем очередном онлайн-лектории «Полимеры будущего», где мы приглашаем известных ученых рассказывать о тех или иных направлениях развития полимеров, полимерных материалов и перспективных их использований. Предыдущие несколько лекториев у нас были замечательные лектора, академики, Музафаров, Хохлов, Берлин, которые рассказали про свои области применения полимеров. А вот в этом году мы решили немножко перевести это в более такую международную плоскость, да, и позвать лектора из-за рубежа, из Германии. Я буду синхронно пока переводить на английском. Dear colleagues, we are ready to see you again in our online lectorium Polymers for the Future, where famous scientists describe different fields of polymers and their application. In the last talks, we have 3 academicians, academician Muzafarov, academician Khokhlov, and academician Berlin, who described their fields of polymer science. And this year we decided to make it more international, and we invited a very nice speaker from Germany, Stephan Kirchmeyer, who is a specialist in conductive polymers. Stephan Kirchmeyer много лет проработал и в науке, и в промышленности, и много сделал для развития области проводящих полимеров, в частности, участвовал в разработке, наверное, самого успешного полимера, проводящего полимера синтетического металла, так называемого Pdot PSS, полиэтилендиокситиофена. И во время своей работы, естественно, познакомился и с другими полимерами, и с применениями особенно проводящих полимеров, вот лидером которых является Pdot PSS, и поэтому, собственно, мы его позвали. Stephan Kirchmeyer worked a lot of time with conductive polymers, in particular with Pdot PSS, starting from its development and upscaling and production at Bayer, and afterwards following companies which produce PEDOT PSS up to now. He made a great contribution in this field. He knows a lot about conductive polymers and their application, and that is why we invited him to our lectorium. And by the way, he's a brilliant speaker. Поэтому давайте мы дадим ему слово и послушаем его лекцию. Мы не раз уже слушали его на своих конференциях и в СОЕ, и поэтому знаем, что он очень интересно рассказывает. Давайте дадим ему слово. Dear Stephan, please, it's your time.
Thank you, Sergey. Thank you also for your very kind words. And today I will give a lecture on conductive polymers for industrial applications. And I have recognized that this is the series of conductive polymers for the future. And the good news is conductive polymers are still polymers which will be used in the future, but we also have to be aware they are not this new anymore. They have been in industry and industrial applications now for more than 20 years already. So just to tell you a little bit of who I am. So at present, I'm retired and I'm still working as a mentor and consultant for small companies and startups to help them a little bit on the adventure, during the adventure of starting a business, which is extremely difficult. And there are many, many traps in which they can fall and to fail. So as you already said, I've worked in the industry, in the chemical industry, with the maybe best known name is Bayer, but also with smaller companies, A.G. Stark, and the last one was Heraeus. And 2016, I quit from the industry. I joined the University of Cologne to do a little bit of marketing for a new institute, which was also meant to be used by startups using machinery which usually startups cannot buy because they are lacking of money. In 2019, I also founded already a company which was highly connected with the COPT Center. And during my industrial life, I've done a lot of work of developing and commercialization of the conductive polymer Pdot, as you already said. And I have to admit, I didn't definitely not do it alone. It was a big team and I was only a small part of it. And I've done also a little bit during my industrial career of publishing and patents. And this is also something in which you could read quite a bit on PEDOT, including, and this is advertisement from my side, the book PEDOT, Principles of an Intrinsically Conductive Polymer. It is already a little bit older, but still contains a lot of things that all the people working on PEDOT have put together. So first question is, what is a conductive polymer? And what makes it different from other functional polymers, also electrically active? Usually, polymers are not conducting. They have a very low conductivity because they have almost no charge carriers inside. And there are various ways to introduce charge carriers. And one of them is just using light. Then we have a photoconductor. And the photoconductors are definitely used in industry. And they are part of the copiers, for example. Then electrical fields would cause charges to jump up in the band, and we would have a semiconductor. And the last one is, which I will talking about, to have a permanent doping. And the permanent doping then would make a conductor which conducts almost like a metal. Usually this works in two steps. First of all, there is a neutral polymer of which one electron is abstracted. There's an anion which needs to counterbalance this charge. We get to a polaron which has an electron, an unpaired electron. And when another electron is abstracted and it's balanced, then we get to the bipolaron, and the bipolaron is usually the state which is very, let's say, the stable state, and it's very common that conductive polymers consist in this state. So one of the, let's say, the challenges of making a conductive polymers is getting to such a state which is stable. So this is done by oxidation, usually by chemical or by electrochemical oxidation, and always is needed to have some counterbalancing, charge balancing counter anions. And this makes this polymer a little bit like a salt. And you will see in a few slides, this salt-like character also has an impact on the properties. First of all, let's go through the conductive polymers which are currently used in industry. And the first one is the polyaniline. The polyaniline can be bought either as powder, as aqueous dispersion, or also as an organic solution from various sources. The properties of polyaniline can be very different, and they are highly dependent on the production process. This is good on the one hand because it is possible to make very different grades, but on the other hand, it's also a challenge because the industry is always asking for a repeatable quality and not a changing quality. And if small changes in the process make large changes in the properties, this is definitely not good. It is described as anti-static agent, and I also know that some people use it as anti-static agent coated on films. By the way, can you see my laser pointer?
Yes.
Sorry?
Yeah, it's possible.
Yeah.
Okay. And what's the, let's say, one of the most promising applications for polyaniline is a finishing agent for printing wiring boards. And it has been also described for corrosion protection, but I think this was not very successful. Polyaniline has a very typical greenish color, which you can see here on this film. And during my life in industry, people that were used to polyaniline wanted this green color back, even with PEDOT. And so some of the customers mixed colors into the PEDOT to make it look like polyaniline. This is just for fun, but this is how these things work. The second conductive polymer is the polypyrrole. It is basically commercially available as monomer and also a little bit as a polymer. It is not this stable. And the polymer can be bought as aqueous or solvent-based dispersion, and it has been definitely used as counter-electrode in capacitors, and we will get to this application in a few slides. And mainly the aluminum and tantalum capacitor, where it's used as a substitute for the typical electrolyte counter-electrode. It also has been used as anti-static agent, but as you can see from this picture, it has a grayish color and it has a strong color, and it makes it a little bit difficult to use as transparent conductor. And so it was for this application not this successful. Last but not least, there is the PDOT, which to my understanding and my knowledge is the most wide used conductive polymer worldwide. It can be also bought from various sources as monomer and polymer, and the polymer is again available as aqueous dispersion. This aqueous dispersion can be here seen in this picture. It's a blue dispersion, and more recently also solvent-based dispersions have been developed and commercialized. Its main application is the counter-electron and capacitors, aluminum and tantalum capacitors. It's widely used as anti-static agent in displays and electronic packaging, and I will show you this a little bit more in detail, but also as an agent which is used for through-hole plating in printed wiring boards. It's slightly blue, and its hue is much less than for other conductive polymers. You can see here on this picture, this is a coated film with PDOT, and as the coating is extremely thin, there's almost no hue visible. This is why it's also used in displays. So what makes a conductive polymer suitable for applications? And you may, because you're working at university, you think that we make a new material and it instantly finds its market because somebody will use it. This is usually not the case. And to make a very long story short, usually it takes 5 to 10 years to establish a new material on the market. And these 5 to 10 years are usually a lot of waiting time and a lot of frustrating time because, of course, the management is asking, why is this material still in your shelf and does not sell as we expected? The reason for that is manifold. First of all, there is usually when we have a new material, we think it is great and somebody should use it, but usually we don't know the specific technical specifications which are normally applied for a specific application. And these, we will get to these a little bit more. These are usually specifications which are not only technical specifications, they are also a little bit more business type specifications. Usually also bringing a new material to market, we see a manifold of potential applications. Out of these, usually, let's say 1 to 3 are commercially successful, not more. This is sometimes also a little bit frustrating because in the very beginning, we as a scientist saying this has so many applications, and then in the end we find out these applications are usually maybe not the scientific most thrilling, but on the one hand, but on the other hand, once we have it on the market, we see that the challenges to keep it there are different than just making a good material. In many cases, to find the right application, despite the, let's say, the wish of the management, is a trial and error approach. And in many cases, it has to be to supply to customers. Customers make trials, and then they find out it has good and advantage properties. This is a little bit difficult slide. I will just try to explain it. My task was to explain a little bit of what are worldwide currently tendencies or market tendencies that help conductive polymers on the market. I will start from the top. First of all, we can look at laptops and computers, at OLED smartphones, e-readers, TV screens, and so on. And you would say, that's great, because OLED may have PDOT in it. Unfortunately, they do not. PDOT has been used in science for OLED, but Samsung has developed their OLED technology only by evaporation without PDOT. And the same is also true for LG with the large screens, TV screens, and so on, in which also just evaporation has been done and there is no PDOT. So OLED doesn't help, but for example, Corona helps the conductive polymers. Why? Because Corona is asking to work more at home, and there was a clear demand for laptops. And at one time last year, they were almost sold out. And laptops need capacitors and printing wiring boards in which the PDOT, for example, or other conductive polymers are used. There's also good news that, for example, TV screens, even OLED TV screens, need PDOT or specifically PDOT because they have a polarizer. Even the OLED TV have a polarizer inside, and they need anti-static packaging. Here down, this is an application, the electrochromic labels and display, which is already existent, but very, very small quantities are sold. It can be used as an electrochromic dye, but that doesn't help us. But I only want to tell you, using such a graph, you could easily and very transparently show which applications help a material to penetrate into the market and which applications are still at the very, very infant state, even though 20 years have passed. So what does the industry usually demand from a material? If I would ask you, you would probably say, yeah, of course, it has to be very beneficial electrical properties and maybe also mechanical properties and so on and so on. And I would say, yes, but this is just a prerequisite. They have to have them, otherwise nobody would be interested. But other than electrical, they also need optical processing, long-term properties, and this is just the technical part. The non-technical part is we have to be able to supply a reproducible quality. If this is not the case, customers will refrain from using it because they have to adjust their processes for every batch, and this is something which is very expensive and they won't do it. It has to be scalable. The industry is very afraid of materials which are not available in a large scale, because what happens if they use more is the supplier says, oh, sorry, I can't do this. And then they are trapped, and then they cannot produce anymore. Of course, also, any material which is brought into the market has to fulfill chemical safety and conformity with existing regulations. And just to tell you what kind of regulations could be possible is PDOT as a material has been listed at one time as material for dual use, meaning material for potential military applications. This made a big problem because every time PDOT was supposed to be exported into a different country, an allowance would be needed from the government in order to make this. And you can imagine customers in Asia don't have a good good feeling if you every time need to get a permission from the government, and that could take time, and the government is not interested in making it very quick. They want to be very, let's say, exact. And of course, which is also always needed, is it has to have an attractive price. Why? Because always customers have an alternative, and this alternative could be better or worse, or it could be more expensive and less. And what they actually is helping very much is if the performance is better, jointly with a more attractive price. If the performance is less and it has an attractive price, this is some sort of so-so. And better quality with the higher price is also very so-so. Usually that doesn't work this well in the market. So let's summarize it. We've seen there's a polyaniline, there's a PDOT, there's a polypyrrole, and each of them has specific applications, which I now will try to explain a little bit. First of all, in order to make a conductive polymer inside a device, we have two options. Either we take the monomer and it could be Pdot or Polyaniline is maybe not very suitable, but it will also work with Pyro. We take an oxidant and then we in situ polymerize the monomer to the polymer inside the device. All we need is the monomer, and you can see on the left side here, this is how ideally Pdot looks like. Usually it is a little bit more yellow than this. An oxidant, solvents, and then we can mix them and use them to polymerize inside something. This is a polymerization that takes instantly part, and iron 3 is then reduced to iron 2. In the end, if we want to separate this polymer, usually iron 2 has to be extracted to rinsed out of the device, which is very difficult. And to make a long story short, usually customers do not really like to make chemistry inside an electronic device. There's a second part to it. The second part is the polymer itself is crystalline. I said it has a salt-like structure, and Olle Ingarnes out of Sweden has made a lot of investigations on that, and he found in a repeating pattern for PEDOT in which we have Pdot strands which stick together and then are separated by the counter ion. And in total, it gives a picture in which Pdot makes stacks like this, separated by the counter ion. And you can easily imagine this works like a crystal or like a salt. And as salts are usually can be seen, they are definitely not extremely good film formers. We can see this in the next picture. Depending on how the polymerization is made, it could be either a good film quality, or it could be, let's say, a moderate film quality. And just by making a simple measurement on these films, one could easily see this has a much higher conductivity than this one. And you can also imagine if you do this inside an electrical device, inside, for example, a capacitor, there's only limited control to either get to this or to this point, while the capacitor is very lousy if we do it this way. The capacitor works very well if we do it this way. And it makes a big difference, and the capacitor industry struggled very much in getting this controlled and to make it in a way that the capacitors fulfill the specification in a repeatable way. So there was a big demand of going away from this and by using preformed polymers to be used as a counter electrode in capacitors. Now let's go to the capacitors. Ideally, the ideal picture of a capacitor is two electrodes, two plates separated by a dielectric with a plus and a minus, and then it can store charges which can be released if, for example, the current is used for something. The motivation of now let's put it like this. In reality, capacitors do not look like this. In reality, the dielectric is absolutely imperfect. It's either shown like here. We have a tantalum powder, which is sintered, which gives the one electrode. A dielectric, which is a little bit of tantalum oxide, which has been done by electrolysis, and manganese dioxide, which is used as the second plate, which is okay, it has some conductivity, but the conductivity is extremely lousy. Or we could look at aluminum capacitors. Aluminum capacitors have are made by aluminum foil. This is etched. After etching, we get this type of surface. Then after electrolysis, we also get aluminum oxide as dielectric. And on the other side of this, we have this plate, which is made out of a liquid with ions. And you could also imagine that this electrolyte has a very limited conductivity and therefore a limited performance. These electrolyte type aluminum capacitors are still on the market, but are accomplished by usually a grade which is called aluminum polymer grade. And if you Google it, for example, or search the internet for these, you will find these type of capacitors from almost every capacitor manufacturer. Approximately in 2000 to 2005, there was a big demand for capacitors with, it's called the ESR equivalent, low ESR equivalent series resistance, or you could better understand it as they have to work at high frequencies. And the second was to use as much as is possible from the capacitor, which is inherently in this powder. For example, a tantalum powder is quite expensive on the one hand, so we would like to use less powder. And for aluminum, they get very bulky. And the miniaturization of electronics asked more and more also for smaller aluminum capacitors. Well, how can we do this? Either by making the electrode area larger, which is by a given powder not very easy. We could increase the dielectric constant. The dielectric constant is also fixed. But we can also try to decrease the distance between the electrons. This is the distance between these two plates. Here it's resembled by the thin tantalum oxide layer, which is inside the capacitor and has been formed by electrolysis. This is far from being perfect. And in case we apply a charge, there could be possibilities that a current flows through this dielectric, which we see in a moment gives a lot of problems. So it is also limited possibility to make this distance smaller and smaller. But we have to keep in mind that the competing materials, the liquid electrolytes and the manganese dioxide, which has been used for the tantalum capacitors, is still in the market and still working. So where is the conductive polymers and the polymer caps? Such a polymer cap could, for example, look like this. This is an SMT type, surface-mounted type of capacitor, of tantalum capacitor. It has the tantalum powder inside. The inside is impregnated with the Pdot and has an outer shell of Pdot, which then acts as the counter electrode. The counter electrode is then connected to one of these. Here we see a picture. This is one of the tantalum grains. It is surrounded by tantalum oxide. And if we look for the Pdot layer is a very small layer which has been impregnated on top of this powder. You could imagine that impregnating here at this point is still very simple, but the deeper we go into the capacitor, the more problematic it becomes. And therefore, making a capacitor using the full capacity of this powder, and on the one hand, and on the other hand, levering the high conductivity of the Pdot, this was a challenge and definitely needed some time to get to a suitable process. So first of all, it was done by impregnating the EDOT, the monomer, and then polymerizing the EDOT inside this structure. Why did people do this? Basically for two reasons. One reason is shown here. if we look to the capacitor versus frequency, you can easily see that manganese dioxide has a problem around, let's say, 30 to 50,000 hertz. While polymers, and the higher the conductivity this polymer is, the higher is also this curve shifted to the right side, could easily work with 1 megahertz. And that was very important to generate capacitors which were used either in computers, which had a more and more high frequency, and cell phones. So these capacitors were definitely one of the keys to get cell phones more and more into the market. And today we could definitely look at the mobile phones, and if we would destroy one mobile phone and try to get to look at the board, we would definitely see a couple of these things which are very small and would be somewhere hidden between other chips and so on the board. What was shown here is the second reason why it was absolutely necessary. It was found that due to the imperfect generation of the dielectric, some capacitors tended to explode. And this was actually like a small explosion, and nobody wants to have such an explosion next to your ear when you phone it. So before the polymer caps came in, let's say when electrical shock was applied to a capacitor, could be, for example, charging this a very small, very fast charge or discharge. A current is generated through one of these cracks. This current generates heat. The heat is then using is causing the metal to react with the manganese dioxide. The metal is a reducing agent. The manganese dioxide is a strong oxidizing agent. And then a chemical reaction takes place. And this chemical reaction between the metal and the manganese dioxide is causing then why this capacitor is starting to burn. So why do the polymer caps do not burn with the same treatment? Very simple. The polymer is not an inorganic material, it is an organic material. And the organic material, when it sees heat, starts to decompose. And what the polymer does first is it loses its conductivity. And when the polymer is losing its conductivity, this current is stopping. So it's some sort, it was called the self-healing properties of these capacitors, which caused the capacitors to remain intact, even though maybe a little bit of the polymer was destroyed, but it was not a lethal problem anymore. The capacitor itself stayed intact and did not catch any fire. The second process I wanted to show you is the metallization of through-hole through holes of printed wiring boards. So we are talking about this part here. We have a ring or something which is connected to wiring on the top, the same on the bottom, and we want to make a metallization through this. This is, and we have basically two options. One is we take palladium catalysts and impregnate it into the hole and use a chemical bath. And this chemical bath then deposits copper on top of the palladium catalyst, and then slowly copper film grows on top of this. This is one way. This is was the established way before the Pdot got into this area, and it worked well so far. There are two problems. First of all, palladium is expensive, and people did not like to use this material too much. And the second was these metallization baths were pretty unstable against any contaminations, and it could easily happen that such a bath is not doing what it's supposed to do. So, and it was difficult to steer these processes and to make them work for a very long time without having much material wasted. The direct metallization process is still used, is used and approximately has 20% of the market, while 80% of the market is still working with palladium. What's happening is this through-hole plating is usually done before the copper structure is developed on top of the printed wiring board. First step is drilling holes, and the holes are then exposing the epoxy resin to the next bath. There's an etch which is done with potassium manganese permanganate, and this is a strong oxidizing agent. What it does is it oxidizes the epoxy resin and deposits a small layer of manganese dioxide. And from the capacitors, we have learned the manganese dioxide, first of all, has a little bit of conductivity, which is not so important, but on the other hand, is also an oxidizing agent. The oxidizing agent is then used together with the monomer of the Pdot monomer to polymerize Pdot on top of the epoxy resin. So there's a small blue layer now inside the hole, and this blue layer is sufficiently conductive that it can be used to directly plate copper on top of it. So then we generate this layer not by a chemical metallization, but by an electrochemical metallization. And this was the, let's say, the motivation to get this into the technology and to use this instead of the palladium. So as I said, both processes are still competing with each other. And to my understanding, the palladium as the established, one of the older established processes, has still the majority of the market, but it works well and is also available from various companies which supply not these printed wiring boards, but processes for printed wiring boards. So now we've only talked about the monomer of Pdot. The polymer itself can be easily made. The monomer is taken, the counter electrode, the counter anion is the anion of polystyrene sulfonic acid, for example, that works very well. With iron or peroxide disulfate, the polymerization is done and we instantly get the fully doped polymer. So together with Professor Banerjee, we have published a method to do this polymerization in a very simple vial. It is intended to be used, for example, in schools, to teach schools and to tell them or to show them, demonstrate them how simple it is to make a conductive polymers and make experiments with it. So as I said, it is not difficult to polymerize, but it's really challenging to polymerize Pdot in a quality which is suitable for industrial use. And it also means that this quality is not the best quality you could do. It is the everyday same quality. And that is also within very limited specifications, the challenge that one has to meet when one is supplying this material for industrial use. One of the main applications for the dispersion of the conductive polymers, besides the capacitors, which is now so used for instead of the monomer, is to coat plastics with the conductive polymer and use them as packaging for either chips or other discrete components for electronics. Now here's a picture of a small silicon dioxide layer with cracks which have been damaged by static charges. And you may be aware that putting chips or just giving static charges the chance to penetrate through chips sometimes destroys these chips, because these thin MOS layers are not able to withstand these charges, the voltages. Therefore, it's necessary to discharge these voltages in a very defined way. So it is necessary to have a conductivity which is very well defined to make antistatic packaging with it. It could be used for displays, it could be used for chips. And the big motivation for using it with chips instead of others like metallization and, for example, carbon black was metallization is too conductive on the one hand. So discharge is going too fast, and it could also lead to destroyment of the discrete components. And carbon black has the problem that sometimes it's ablates and forms bridges between the little legs of a chip, and it has a shortcut. And the last one is inorganic salts. They're very inexpensive, but they are moisture dependent. They need water to have their antistatic effect. And of course, if you run a company which assembles chips and you experience different environments, like today we have very dry weather, tomorrow it's very humid, you don't want to change your products day by day. And having maybe one day 100% yield, next day only 50% yields without really knowing why. As I said at the very beginning, one of the applications is in displays. And many of you may have thought, no, he's talking about OLED. No, I'm talking about the traditional liquid crystalline displays. And I want to show you here with this picture, where is the conductive polymer located and why? It is maybe also a very little bit difficult slide, but I will try to guide you through. First of all, in the middle here, we see this is the display itself. It has a color filter on the top. It has the TFT glass substrate on the bottom. In the middle is the liquid crystal. And even though it looks like we have many, many layers over here, each of them consists of several layers. Specifically, the TFT glass substrate has also the transistors on top of it. On the sides, we always have a polarizer into two areas, into, let's say, two directions. And the polarizer is specifically needed for the LCD display to make the LC effect. The polarizer consists of the PVA, which is a very soft polymer containing the iodine. The iodine is then used as the let's say the polarizer itself, because iodine penetrates very, very efficiently into the environment. It needs to be sealed by something, and this is the so-called tech film. This is the cellulose triacetate film, which is a very old polymer, but very effective to shield the PVA from the outside. On the top, we have a protection film, and the protection film will be removed during assembly, and the top of the protection film, in order to avoid dust, there's a small anti-static coating on the one hand, and on the second hand, between the tech film and the PSA is a pressure-sensitive adhesive, the glue that glues the whole polarizer on top of the display. Again, is a small film of conductive polymers. So why is it there? Very simple. In order to when the whole film, these whole films are processed, and in the end we will have a so-called polarizer film, which consists of all these different structures. There may be charges trapped over here. And these charges, when the polarizer is assembled to the liquid crystalline display, will cause a field, and the field is causing the liquid crystallines to align. We do not want that. We want that the liquid crystals align to the TFT voltage and not to a voltage that is trapped in the polarizer. Therefore, we need an anti-static coating in between before the polarizer is glued on top of the liquid crystalline display. The same is also on the other side, but I've not shown this fully here because it's basically the same polarizer, just in a reversed order of films. A little bit to the morphology, and I think I will hurry up a little bit to make it to have it ended after 1 hour. We always knew that Pdot PSS is consisting of little particles, and it took a long time to find out how these particles look like. And Udo Lang, who made these pictures in 2009, helped us quite a bit to understand this. So the Pdot itself has PSS strands, which are somehow connected to the Pdot strands. They look like these, and we can understand them as a particle which has PSS on the outside, enriched PSS, and enriched Pdot on the inside. This works like an insulator. If this is an insulator, so what happens? Very simple. If we are able to get rid of this insulator, the conductivity will become much higher than if we remain this. And what's happening with certain solvents, with very polar solvents like DMSO, N-methylpyridone, or ethylene glycol, is that these solvents are able to dissolve this layer in between and get the Pdot in these particles to interact much better. It is some sort of recrystallization process, and sometimes in a microscope it can be even seen. But the macroscopic effect is very simple. If we take various grades that, for example, can be bought on the market and measure their conductivity just by making a coating and measuring, then we measure values of 1 or let's say a maximum of 10. If we mix these solvents into the formulation coating, heat it up, then suddenly the conductivity jumps up to a factor of 100. And I know that many scientists which have worked with OLED sometimes were very puzzled about this effect, and also were not aware of this effect, and found that the conductivity of something inside the device, if not controlled right, were much higher than they expected. And usually, when I was asked why is this, I was asking, what did you use as solvent? And in many cases, I found that somewhere they used these type of solvents and were astonished that this happened. And this is the reason behind it, that these layers, these PSS enriched layers, are somehow dissolved, and the Pdot inside the particles can much better interact with each other. There have been attempts in the literature to make the conductivity as high as possible, and there are up here were reports with more than, let's say, 3,000 to 5,000 Siemens per centimeter, which is material specific value. Commercially, approximately 1,000. To compare this to real conductors, 1,000 compares to copper of 70,000 or silver to 200,000. So they are conductive. They are nicely conductive, but definitely much less than metals. Second is, we can see this effect of the energy barriers between these particles by looking at the temperature dependence of conductivity. And you can see that the higher the temperature, the lower the resistance, that meaning the higher the conductivity. And interestingly, this is to a certain temperature, this is reversible, but starting from a certain temperature, this is also irreversible, which means this effect of rearrangement does not only take place with a certain solvent, it also takes place just at a certain temperature. Out of these curves, it was extracted that the jumping of holes inside such a polymer is a hopping of 1 to 4 to 2 nanometers. This is for the scientists. Last but not least, I will also mention that PEDOT was proposed to be used for OLED, solvent-based OLEDs. It works. It has two effects. First of all, it increases the hole injection, but it also smoothens the layer and has a lower leakage current. If we reverse this OLED and look at it from a different side, we have a photovoltaic element, a solar cell, and then PDOT is used basically in a very similar setup as an acceptor layer and together with an absorber, which makes the charge separation. I will not go too deeply into this for the following reason. I'm talking today about conductive polymers of industrial use. And these are very nicely and much work in science has been done on these devices, but we have to be aware that none of these really has made it into a mass production yet. Last but not least, one aspect which is interesting to know, because you can use then the PDOT also as electrochromic color, and Sergey has done quite a bit of work on this, and when he was working in Germany. As I already said, PDOT is sometimes a neutral material. This is the undoped and has two states: the reduced state, so-called the polar one, and the typical state as a conductive polymer, the bipolar one. It changes its color starting from the conductive polymer slightly blue into deep blue. And when it's the semiconductor has a totally different color, it is more violet or purple. Again, this is nothing that has been penetrating into the industry. I just mention it here as a property of the PDOT, which can be possibly used as property for applications. There have been many things that have been proposed and tried, and a lot of work has been done. So there were many opportunities, like organic LED in cars in red, organic LED lamps that have been made, the solar cells, displays with conductive polymers as electrode to steer these displays. They're very attractive for scientific work. Many expectations have been based on this, but we still have to be honest that there are still hurdles to be overcome. And from my point of view, I'm not seeing any, let's say, tendencies now to get any of these applications into a mass market. I hope that this will change, but after 20 years, it is not an easy application anymore. So I will now get to my conclusions. Just recently, I read an article in which it was said conductive polymers is a new class of materials. And I had to say, no, conductive polymers are not a new class of materials. They are still a class of materials which have their place in future and will be used in industrial processes, but definitely not. They're 20 years old. And sometimes there's a mismatch between what is actually done in the industry and what is done in science. And I think here it is this. In the science, there's still the, let's say, the view that many new things can be made with conductive polymers, and this is true. But the conductive polymers themselves are definitely not new materials anymore. They are in many cases hidden in their application, and today I try to make it a little bit more transparent where you find these materials and where they are really used in mass production. They're used definitely in aluminum tantalum capacitors in a wide scale. And I think the majority of conductive polymers will be found when you start to look inside the electronics of your mobile phone. Printed wiring boards, in flat screens, and very thin films used for antistatics, and in electronic packaging. There are many more devices like organic LED, solar cells, and other devices that were of significant interest. And I followed all this for many years, but we have to say but. And if you look now at the scientific literature, I think also in science, more and more people have lost interest in conductive polymers. And more they have become established materials. This is my last point. I thank you that you have been listening to me. And I specifically thank to Sergey that he has invited me to give this lecture. And I would be happy to receive questions and remarks from now on. Thank you very much.
Thank you very much, Stephan. It was very interesting. Actually, the limit of participants was 100, and we almost, during lecture, we have, almost 100, and all the rest were listening, following your lecture in YouTube.
Thank you.
So now we have time for some question or discussions. You can ask question by raising hands in Zoom using reaction, or you can write it by chat, or even in YouTube, you can write it in the comments. So I see the first question comes from Professor Aziz Muzaffarov. Please.
Thank you, Sergey. Thank you, Professor Kirchmeyer, for the very nice and comprehensive introduction to the field. And I'm exactly want to ask a question which you just exclude because still there is not industrial application concerning sun batteries. And really interesting in the prospect of polymeric sun batteries. And the question is why they are still not on the market, because there is no market demands, or just because of some complication. I'm just understand that the efficiency it's still lower concerning the inorganic sun batteries, but the benefits of polymeric sun batteries, they are just cheap. In general, in principle, they are cheap, and also we can use huge squares somewhere in a good place. So, what your vision of prospect of this field? Whether we could consider it as a promising or a reliable area for the getting energy from this source, or this is still just dreaming?
This is let's say a question which is not easy to answer. First of all, yes, the batteries made out of conductive polymers have been in investigation now for a very long time. And you're absolutely right. Somehow, for whatever reason, they have not been adapted. I think if you remember the picture of this lousy picture with the S-curve and so on, then it is maybe necessary to look at if we think conductive polymers as a battery, what is the actual demand for batteries, and what are the tendencies driving the demand for batteries? And one of the big demand for batteries currently are electrical vehicles. And for electrical vehicles, we currently need more and more energy stored inside let's say the battery. And the factors are weight, the energy that could be stored, and safety. And if we look at all the properties of conductive polymers, they are cheap, this is correct. But the energy that could be stored in a certain way, in a certain weight, is not sufficient. The second part is, if we think about electrical vehicles, the ability to be charged and discharged several 10,000 times. This is very, very important for a car, because the car, inside the car, let's say people do not want to change the batteries all the time. Therefore, I see that people hesitated to use conductive polymers for this purpose. Also because conductive polymers would be needed to be, let's say, used as a thin film. And then the carrier of this conductive polymer would add a lot to the weight. And after doing these calculations, people always said, no, this is bad. You're absolutely right if you say, if we look at current lithium batteries, the weight is usually manganese, nickel, cobalt, and a lot of metals. And one has to do very, let's say, careful calculations in order to judge this. All I can say is we can discuss this, but at present, I don't see any attempts to use this in this area.
Thank you.
Okay, any other questions? Actually, Stefan, I have a question concerning the PEDOT as one of the famous conductive polymer. What is actually now the volume of production of PEDOT in the world? You probably know the figures.
It's very difficult, because you may have seen I'm now out of this business for more than 6 years, and therefore I've also lost a little bit. But I know that besides in Germany and in Belgium, several companies in Asia, Japan, Korea, but also China produce PDOT. and also EDOT. That means the minimum that we can calculate of industrial production is several hundred tons of polymer.
Mhm.
So it's definitely more than a laboratory can supply within a month.
Do you mean tons of polymer or tons of the solution?
Tons of solution, but tons of solution is also now easily, let's say, tons of polymer.
Okay. Yeah, thank you. Any other questions or comments from our PhD students? Yeah.
Can I also ask a question?
Yeah, Daniel. Yeah.
Thank you very much, Stephan, for such an interesting talk. I have a question on how many applications did you work on in parallel? I mean, you have talked about like 5 or 6 applications of Pdot, and how many time did it take to realize that it's a prospective application, and like how many of them did you do in parallel? Or how do you did you open these ideas, because some of them are not obvious at all?
Mm-hmm. You can imagine this as, let's say, like a funnel. In the very beginning, nobody had a clear view of how many applications are there. So there was a whole continuum and universe of applications, and the big challenge was, which one of these should we put our effort on and which not? The only way to do that was starting with certain applications and then try to figure out what happens. So the first applications was somehow the antistatics, OLED, OPV, and so on. Then the electrochromic came with it, and in the end we found we have not the capacity to work on all of them. And then after a while, let's say a while is maybe 5 years, we also find out that some of them are more attractive than others. And it is like it works in industry. We started projects, and after running out, we had to decide, do we want to continue or do we want to leave it this way? And then it was a question of what was the more recent progress within this project? And if the progress, if we had the feeling it's somehow stuck, we said, let's drop this application. And let's wait, maybe there's a certain demand at one time, then we can again try to give this up. To give you a number, in the very beginning, it were maybe 20 to 25 different applications which were worked in parallel. And in the end is now currently maybe 3 to 4, maximum of 5 applications.
And then continue this question, what is the most actually important application, the most mass production application of PEDOT now?
For PEDOT.
PEDOT, yeah.
Capacitor.
Capacitor.
Just rough figure. I don't know any sales number anymore, but my just rough estimation is 70 to 80% of PDOT go into capacitors.
And what is the next?
Antistatics.
That's great, antistatics.
Yeah. And then the next maybe something like printed wiring boards, but again, this is already quite small.
Any other questions, comments? I don't see any more. Okay.
Everybody who's listening today and is hesitating to send a question is also welcome to send me an email. On the last slide, my email address was shown, and if people can also open it at YouTube, they can see my email address.
Okay, thank you, Stephan. I see we have a hand from Sergey Vasilyev.
Yeah.
Yes.
Question about capacitors. You said that you use them in computers and cell phones, but they need more and more frequency and higher frequency. So 1 megahertz is quite low frequency, but can the capacitors be more higher frequencies?
Yeah, it's really depending on which application it is inside the cell phone. You're right. For the current frequencies that are used by cell phones is not suitable. But for example, if you have it as backup, the capacitors which are made by polymers are usually capacitors which have a high capacity. And they are used as backup capacitors, for example, to enable the battery to be very stable, or for notebooks also to as a backup capacitor for the central unit. So in this case, 1 megahertz is okay.
Thank you.
Okay, do we have any other questions? If not, then thank you, Stephan, for delivering this excellent lecture. I think you will receive some more questions by email, and your lecture will be also available in YouTube, and you can look some comments after that.
Sure. So everybody is highly welcome to send me questions.
Yeah. Thank you, everybody, for joining our online lectorium, and see you next time, somewhere in 3 months.
Yeah. Bye-bye.
Thank you very much, Stephan. Bye-bye.